Hi, I'm Grace, and today I'll be presenting our project, Shape-Guided Diffusion with Inside-Outside Attention. First, consider this real image. What do you think is a plausible edit for the object highlighted in the black mask? Many methods would simply inpaint the mask such that it blends with the background, meaning filling the region with more floral couch. However, when a user inputs the contours of an object, as opposed to a blob, it often means that they are trying to convey something specific. In this case, it is often more desirable and intuitive to the user to replace the region with an object as opposed to inpainting with background. In fact, given the object's silhouette, a dog seems the most likely. We demonstrate that much of prior work struggles with this shape-guided editing task. Even methods specifically trained for mask condition inpainting, such as ST inpaint, highlighted in yellow, struggle with understanding the semantics of a precise object silhouette, and it adds a smaller dog and inpaints the rest with background. On the other hand, our method is most faithful to filling the input mask. Our method for shape-sensitive editing is derived from the observation that the internal attention maps of the diffusion model are directly tied to the shape of the synthesized object. On the left, we display an image generated with the prompt dog, and on the right, we display the cross-attention map for the token dog, averaged over all attention heads, layers, and time steps. Although the token dog has the strongest activations over the dog depicted in the image, it also tends over background regions, such as the flowers. In the editing setting, where we may only want to edit the object, it seems rather undesirable for this dog token to influence the background region that we would like to stay static. As a result, we introduce a mechanism that constrains the attention maps according to the object silhouette, such that this token dog no longer tends over the background. We introduce a training-free mechanism, which we call inside-outside attention, to apply this constraint. In the cross-attention layer, the attention operation uses the image embedding Q and text embedding K to compute the attention maps M that represent the relevance of each token over the image, which is then used to contextualize and update the features of the synthesized image before it is passed to the next layer. To apply the shape constraint for tokens that refer to the object, or inside tokens, we simply multiply the attention map with the object mask to zero out attentions over the background. In the case of tokens that refer to the background, or outside tokens, we instead multiply by the inverted object mask. We perform a similar operation in the self-attention layers, where instead of contextualizing with text token embeddings, we now use pixel embeddings. We again, for inside pixels, or those within the object, multiply the self-attention map with the object mask. For outside pixels, or those in the background, we multiply with the inverted object mask. We apply this attention constraint during both the inversion and generation process. Because we're editing real images, we find it is helpful to first run DIM inversion, which discovers a noise seed that would reconstruct the input image and is then used as a starting point for our generation process. To edit the image, we then run generation with a different text prompt, i.e. from dog to dog wearing a colorful shirt. Here, we depict some results from shape-guided diffusion. We might want to go from a bird to a bird with blue and yellow feathers, or from an elephant to an elephant wearing Christmas decorations, or from a bear to a bear wearing sunglasses. Note that we only condition on the shape, not the pose of the original object, so it can result in cases where we synthesize an object with a different pose but valid shape. We think that this behavior is quite interesting because for more ambiguous shape inputs, we can explore more diverse edits. Our method can not only handle precise object silhouettes, but also noisy inputs automatically inferred by an off-the-shelf segmentation model. In this case, our method is able to handle cases where there are multiple overlapping objects, for example, horse to futuristic biomechanical robot horse, or from boat to inflatable boat, a challenging case where our method not only edits the boat, but also its reflection in the water. We can go from a truck to a Lego truck. Our method can not only do intra-class edits, for example from this cow to another cow covered in gold and diamond chains, but also inter-class edits, for example a cow to a sheep. Our method is not limited to object replacement. We can also do simultaneous inside-outside editing, where we edit both the object and background, but still respect the shape relationship expressed by the input mask. For example, going from this horse to a futuristic biomechanical horse and changing the background to the Big Ben in London, or changing the background again to the Met in New York City. We can go from this dog to a dog dressed as a Jedi in the Kingdom of Naboo, or a Jedi in The Hobbit. We can go from this cat with some bottles into a cat wearing sunglasses in a coral reef, or at a sandcastle at the beach. We conduct an annotator evaluation where we ask people to compare the edits made by different methods in a blind fashion. Specifically, we present annotators with the input image, text prompt, and mask, and 3 different images produced by 3 different methods in random order. The methods are our method, prompt to prompt, a work for structure-preserving editing that does not require a mask, and prompt to prompt plus shape, a modified version that applies a shape constraint by copying the background of the image at every time step. We also ask folks to rate the method along a few metrics, including shape faithfulness, meaning does the edited object match the scale and silhouette of the original object. As seen in these results, our method is preferred the most, 2 times more than the best performing baseline. We also ask annotators to rate text-image alignment, i.e. if the edited object matches the text prompt. Our method is again the best, and it's preferred 1.6 times better than the best performing baseline. Finally, we also ask raters to annotate image realism, i.e. if the edited image looks realistic and lacks visual artifacts. In this case, prompt to prompt actually performs the best, but often because it completely ignores the real image. This is also reflected in the fact that its FID scores are often much higher, meaning that the images that it produces significantly diverge from the distribution of the original MS Coco images that they're editing. This is reflected in the fact that our method is by and large preferred as the overall best editing method because it is faithful to the original input image while doing a very subtle object replacement, which prompt to prompt significantly struggles with. Our method is selected as the best performing method 2.7 times more than the most competitive baseline. In conclusion, we identify a limitation with prior work where they often struggle with shape-guided editing. To remedy this, we introduce a training-free mechanism that applies a shape constraint on the attention maps at inference time. Our method, shape-guided diffusion, achieves state-of-the-art results in shape faithfulness, where our method is preferred 2.7 times more frequently than the best performing baseline. Thanks for listening, and for more details, please visit our website.